Okay, so we have a very special speaker today, and the amount and the variety of the audience tells for itself. So probably we don't need to list the whole list of prizes and so on of the speaker. We should just allow him to speak about mathematics. So please, Peter Scholze.
Thanks. I should make two announcements. First of all, I didn't give a seminar talk in about a year. And second, it's my very first Zoom talk. So let's see how that goes. Right, so the title of my talk is the categorical form of Fargues conjecture.
Peter, I'm very sorry. Maybe you could move a little bit the list to the top.
Well,
yeah. Thank you.
And okay, so what is this about? So it's so there's a version of the local language correspondence. And so what's the data that we are interested in? So we start with G over QP, or really any other non-Archimedean local field. But let me stick to QP for simplicity. Be a reductive group. And really, just for simplicity, I want to assume that G is split. Okay, so so in local Lagrange, we are interested in really the category of smooth representations of G, smooth representations of G of QP. Okay, and so usually the way local Lagrange is done is that you don't really study the whole category, but you're really studying the irreducible objects in this category, and you're trying to classify them in terms of L parameters. So the usual story. Is that there exists some canonical map. Maybe I should say, when I study the smooth representations, let's say they are in C vector spaces, where C is some algebraically closed field of characteristic 0. And let me actually already now choose C to be QL bar for some prime L not equal to P. Okay, so that there should exist a canonical map of the irreducible smooth representations.
Sorry, what is a smooth representation?
Okay, right. What is a smooth representation? So that's a C. That's a C vector space V with an action of G of QP, such that for all V and V, the stabilizer of V in G of QP is an open subgroup. So it's somehow an action that's continuous when you put the discrete topology on V.
Why the word smooth?
It's a standard name that is stuck in this kind of representation theory. Locally constant functions are certainly smooth on something totally disconnected. So, yeah, I think it's mostly for historical reasons, but I'm happy to stand corrected. So the irreducible smooth representations, they should map to what are called L parameters. So these are certain maps from the Weil group of QP to the dual group of C, G, to conjugation. Denoted, I don't know, pi maps to phi pi. Where I should, in a second, I will recall the objects that intervene on the right hand, on the bottom part of this thing. And this map shouldn't quite be bijective. For GLN, it should basically be bijective, but for other groups, it's worse than that. And so usually, the way this is stated is that the fibers should be related to the representation theory of some group S phi, where S phi is the centralizer of phi, which is a subgroup of the dual group. So, at least for some of sufficiently generic representations, the fibers of this map should be in bijection with a certain subset of the category of representations of the centralizer group. So, conjecturally, there is some relation between these representations of G of QP and these so-called R parameters. So let me briefly recall the objects that intervene here. So there are two things that intervene. One is somehow something of arithmetic interest. It's a Weil group. So what is this? So recall that if you look at the absolute Galois group of QP, then this has a natural filtration where the simplest representations are the simplest extensions of QP are the unramified representations, unramified extensions. They correspond to extensions of the residue field, so they correspond to the Galois group of the residue field FP bar, which is canonically the head generated by the Frobenius. And you can simply take the preimage of the you have the integers in here generated by Frobenius, and you can take the fiber product, and this would be the Weil group of QP. So it's some partial discretization of the absolute Galois group of QP, where you somehow remember that there's really a canonical Frobenius in this unramified quotient of QP. Right. So that's one ingredient in these L parameters, basically the absolute Galois group of QP. The other is the dual group. The dual over C is a reductive group whose root data are dual to the root data of G. So this is usually defined by this purely combinatorial recipe where you extract this combinatorial data, the root data from your group G, simply exchange roots and co-roots, and build a new reductive group. So, I mean, the dual group of GLN is GLN, but if you take the dual group of SP2N, you get SO2N plus 1, for example. So, when I first heard about this local language correspondence, the things I really want to understand is how the hell does the dual group appear? I mean, this is not defined by some nice construction, it's just combinatoric. And how the hell does the Galois group enter this picture? And so today I want to partially explain where this will come from in some kind of geometric way. Right. Okay. So what Fargues conjecture will amount to is in particular an upgrading of this local language correspondence, which is just some other classification of the irreducible objects, really to a categorical statement describing the whole category of representations. And I decided that I will just state this conjecture right away and then explain all the terms that appear in this conjecture. So it will relate two things. One is some kind of category of L-adic sheaves with, say, QL bar coefficients. And let me put some finiteness conditions here. Sorry. So this looks like the kind of, for a scheme, you always know what DBC, this QL bar coefficients, is supposed to be. It will actually be not so clear what it will mean in this context, but main claim is that you can make sense of this. This should be equivalent to something on the dual side. Again, some dB, and this time of some coherent sheaves, of something I will simply call X G check. So, and here there will be a functor I will call J lower shriek, which will embed the derived category, the bounded derived category of finitely generated smooth representations of this of a periodic group. So this is what we're interested in. There will be a canonical fully faithful functor into this more geometric category of sheaves on Bun-G. And this in turn should be equivalent to the derived category of coherent sheaves on some stack XG check. So
sorry, what is Bun-G?
What is Bun-G? This will be one of the main mysteries. I will come to it. Okay, so need to explain. And let me this time actually start on the right-hand side, because the right-hand side is the more elementary one.
Sorry, finitely generated means finite dimensional or something else?
No, finitely generated means, sorry, so the generators here are the compactly induced representations from some compact open K to G of QP of just QL bar as a constant representation, where K is some open subgroup. So this is, if you think of representations of G of QP as modules over some Hecke algebras, then this would really be the finitely generated modules over these Hecke algebras. And maybe I should say that, like, there is some of this composite functor that composing the two, you can forget completely about what this Bun-G is. And it's just saying that there is a fully faithful functor from the derived category of these representations that we're interested in into something, into these coherent sheaves on the stack XG check, which will be just a stack of L parameters. So in one word, this XG check is a stack of L parameters. And so in this way, it's saying something reasonably concrete. And I should say that the fact that there should be a fully faithful embedding like this is, as far as I know, was, I think, first suggested by in a conjecture of Hellman. So he was mainly considering maybe the principal block, but maybe for this kind of conjecture, that's actually, if you combine it with usual Langlands conjectures, maybe the most relevant part. So, right. And so.
And is there an adjoint functor for this fully faithful embedding?
Yes, so I mean, this is some kind of J lower shriek functor, and so there's definitely a right adjoint, which would be a J upper star functor. And
what is its kernel?
Its kernel is huge. So this category upstairs will be much, much bigger. So roughly the picture is that we will have some stack Bun-G. And you can think of it as a little bit like the stack of G bundles on the projective line. And so it has lots of points corresponding to lots of different G bundles. But there will be the semi-stable locus, and there will be the trivial bundle. And the locus where the bundle is trivial is an open substack for P1 at least, and it will also be an open substack in this setup. And the this fully faithful embedding will be those sheaves that are concentrated at the trivial G bundle. But then there's all the other G bundles also in play. And somehow to get all the covariant sheaves on XG check, you actually need all these other points of 1G. I should also say that 1G is not at all an object like in the familiar geometry. It's not an Artin stack or anything like this. It's a very fancy kind of geometry. Let me first study the right-hand side, which is much more classical, and then come to the left-hand side. So I need to explain what this XG check is. So it's a stack of L parameters. Maybe another thing I should have said in this conjecture is that to get this functor canonical, I need to fix Whittaker data. So that's some kind of standard choice you make. So that's a datum of a Borel G and some co-character, sufficiently generic character of the unipotent radical of this Borel. For GLN, for example, this choice is unique up to isomorphism, but like in general, you should better fix it to get a canonical. It always exists. So I need to explain what on the right-hand side this stack of L parameters is. I need to explain what this Bungie is. This will be the stack of G bundles on the Fargues curve. And I need to explain, this is something I promised in the abstract, that I will also say something about the analytic formalism, which is not so trivial to obtain in this case, and discuss what this category of analytic sheaves on Bungie is. Okay.
Sorry, Peter. So C capital is QL bar, right? I'm sorry.
QL bar, the coefficients.
No, I mean for Whittaker data you fixed.
Yeah, I mean this. Yeah, C is equal to QL bar. Yeah.
C is QL bar. Okay, thank you. Maybe it's possible you might write a little bit larger, please. Okay.
Sorry, yeah, because I had to.
Yeah, I see.
Sorry, yeah.
Okay, thank you. Sorry.
Yeah, if I have to add something, it might get smaller. I try to write big. Right. So let me start with XG check, the stack of L parameters. Right. So this is actually something where it will be important in the way I formulate it to work with QL bar. So the way I will set things up, it will not work over any algebraically closed field of characteristic 0. So the thing I will define on depends on working over an analytic field, although up to isomorphism it doesn't, but anyway, it's a subtle point. So want an algebraic stack. So Artin. Whose QL bar points are all the continuous maps from the Weil group of QP to G check QL bar somehow up to conjugation. It's this groupoid. Okay, so what's weird maybe about what I'm writing here is that I'm slightly mixing two things that seem incompatible. Namely, here I asked for continuity, and I really endow here the analytic numbers with their topology, and I also endow the Weil group with their canonical topology. But on the other hand, I want some algebraic stack. So this would rather indicate that I want to have my algebras that I put in here regarded as discrete QL bar algebras. And there seems to be a mismatch here. The claim is that it's still possible to define such an algebraic stack. So let me try to discuss this. Right, so to discuss what's happening here, let me recall a little bit the structure of the Weil group. So the Weil group, as we discussed, it has this canonical quotient given by the integers, and the kernel of this is called the inertia subgroup. But then the inertia in turn has a tame quotient, which is just a product of copies of ZL, or really ZL twisted by 1. Tame quotient. And then there's again a kernel called the Wald inertia, which is pro P. And what happens when you consider these continuous representations here is that the pro P subgroup, it must act through a finite quotient, and also all these factors here, except the one parameterized by the same L, they must act through a finite quotient. But then there's this one ZL factor here, which is somehow compatible with the L homology on the target. And this is somehow allowed to act via some interesting kind of unipotent action. And this unipotent action can really vary algebraically in families. And this is what we want to allow. So, and here's some way to define this. So here's the definition. So let's say A is any QL bar algebra. Then I make the following weird construction. I endow A with the following topology. So I can write A. I mean, in particular, it's a ZL module, right? So I can write A as some filter colimit where the MI are finitely generated ZL modules, right? As any ZL module. And I can endow those with the L topology. That's a perfectly natural thing. You can put on a finitely generated ZL module. And I endow A with the direct limit topology.
This is called the dir-inv structure.
The what?
Dir-inv structure.
In
some papers of mine, Ikutieli.
Sorry, I need to look who's speaking. Roma, sorry, who's speaking?
Dir-inv structure.
Okay. Okay, thanks. I didn't know this. Okay. Dir-inv. Is that what you
it
said?
might or might not be complete.
Hmm?
It might or might not be complete.
Right. Actually, I usually think of this in slightly different terms where, I mean, with Dustin Clausen, I developed this condensed mathematics that will also come up a little later in the talk. And so in condensed mathematics, it will be the following. So you take A as a discrete algebra, and you tensor it over QL bar with its discrete topology, with QL bar with its natural topology. This is some operation you can do in condensed strings. And this is some of the topological incarnation of this. And for what I'm saying right now, it doesn't actually matter that whether you switch to the condensed setup or not. Later in the talk, it will actually be somewhat relevant, this condensed. Right now, you can say it in these topological terms. In the condensed setting, it will actually be complete in whatever notion of completeness we have around. Okay. So you can endow A with this topology, and then you define.
It is sometimes called a Tate structure in case the direct limit is countable. A Tate space by Grinfeld.
Right. Right. But you can also do this for if it's uncountable. Yeah. Anyway, it's some topology you can put on any QL bar algebra. I mean, actually, whenever, like on, the way I like to think about it is that whenever you have any condensed string, then the usual discrete modules actually embed fully faithfully into the modules over this condensed string, into the condensed modules over this condensed string. Why is this kind of functor of tensoring from the discrete ring to the ring with its topology? And anyway, something you can do. You can define XG check to be the thing that takes any such A to, and now I can just write down the same thing. Continue such maps. I mean, I should say the sheafification of this. Okay.
Is A commutative?
Of course. I mean, I could make this definition even for a QL bar module up there, but right now, I mean, this is a commutative algebra. I want to define art instead. And okay, so the point is that somehow by putting this topology on A, we're somehow allowing the analytic inertia of the wave group to act via interesting unipotent actions on G check. Okay, and so the theorem and I believe this is actually, I was told recently that this is actually work in progress by a few people. Jean-François Datt, David Helm, Gilbert Moss, and I think I forget somebody, I'm sorry. That this XG check is actually an Artin stack. So actually, if you forget about quotienting out by the G check action, it would just be an algebraic variety. So this is an algebraic variety. It's a locally complete intersection. It's reduced. Do I want to say something more about it? Yeah, so it's a reasonably nice gadget.
Is it easy to see all these properties?
It's not too hard to see. So the, if you would look at the simplest kinds of parameters, then that somehow are where the wild inertia acts trivially, and maybe also all these quotients except the one corresponding to L act trivially, then such representations would be given by just two elements in here, a Frobenius element and a generator of this term inertia. And these two elements, in order to define a group homomorphism, just need to satisfy one simple commutation relation. And this will define a complete intersection as soon as the variety is of the correct dimension. And to prove that it's of the correct dimension, the main input you need is that there are only finitely many unipotent conjugacy classes, which is a theorem of Lustig in general. So actually, I should say that I was working here over QL bar, but actually everything works integrally. So it works over ZL instead. And actually, the same comment applies to the whole talk. So also the categorical form of Fargues conjecture can be stated with ZL with integral coefficients. And then it will actually also not just say something about local Langlands with for representations in characteristic 0, but also for mod L representations of these things.
I'm sorry, can I ask a simple question about the definition?
Yeah.
So let's just leave a copy of ZL in the V group, and let the target be let the target be GM, the multiplicative group. So it seems that the gadget, and forget about conjugation. So the gadget has no field valued points. So like, I mean, the only QL bar point is 1.
Sorry,
but,
what? No, for GM?
Okay. Yeah, so the target is GM.
There's still the Frobenius, right?
Let's forget about the Frobenius. Let's just only leave ZL of 1.
Okay.
Yeah. So then,
well, you can
the
still
variety.
X through a non-trivial L's root of unity, right?
Pardon me?
You can still X through a non-trivial L's root of unity.
Yes, but but I'm looking at the kind of continuous part. Yeah.
Okay. Yeah. Right.
So then, well, if you're looking at A being QL, you have only 1 point. But then if you take the algebra A to be dual numbers, you see more. You see the full tangent space. So I'm confused by that. So somehow.
No, you actually don't, because of this commutation with the Frobenius.
So the Frobenius is important. So we cannot do it without the Frobenius. Is that what you're saying?
So there's actually something funny. So this you could try to define it. So the way I gave the definition, this thing is actually not an object of derived algebraic geometry, but really of algebraic geometry. I somehow only defined it on discrete algebras, right? I mean, discrete in the kind of homotopical direction.
Yeah.
A priori, you might think it would be better to possibly allow higher homotopical information to make it a derived scheme. And I think usually this would happen for GM for a smooth projective curve. Does it?
Can you say one more time?
Your log cis usually
it's derived for GM, yes.
Yes, right. So the issue is that right. So here you could, I mean, if you do it with this topological thing, you can't actually naively try to define it on derived algebras. But if you use a condensed formalism, this actually allows derived algebras all fine. So you could define this as a derived stack, but then it will turn out to be classical. And this is different from the usual situation of geometric Langlands. And the issue is that in this situation, it's actually true that the group cohomology, let's say, of the absolute Gauer group of QP with, I don't know, ZL coefficients is actually isomorphic it's isomorphic to the R-HOM from its abelianization to ZL, maybe shifted by once or something. In other words, somehow you can take the absolute Gauer group of QP. Oh, sorry, let me say it differently. You can take the V group of QP. And okay, the classic effect in class field theory is that the abelianization of this is actually QP cross. But this is actually true in the derived sense. Which in more elementary terms is somehow relates to this statement that the R-HOM is actually equal to.
I see. But okay, but the point is that the Frobenius is important. If you didn't have the Frobenius,
is important.
Thank you very much. Yes, that was the confusion.
Yeah. Okay, and so, right, so this way you get a completely canonical kind of stack of L parameters. And note that in the way I've now defined L parameters, something actually didn't make much of an appearance that usually makes an appearance. Namely, the Weber-Lien group didn't really make an explicit appearance. So usually, one makes this transition from the Weil group to some of the Weil group times an additional GA or something like this, and it looks like representations of that, because then you've somehow, I mean, if C was the complex numbers, then this analytic inertia could also not act via something unipotent. Then you need to put something extra in to let to get this unipotent action to survive. You don't actually have to do this over the analytic numbers, and yeah, so you get something like this. It's completely canonical. The generic, I mean, you can rewrite this in terms of these other ways to define R parameters in terms of Wertolin representations, putting some discrete, really using discrete topology on Q bar. But the isomorphism between these two varieties is actually not canonical. It depends on some auxiliary choices of Frobenius element and so on. So really, the most canonical thing seems to be this, but this depends on L. Okay. Right. So, yeah. So that's one side of the story. So let me actually maybe. Oh, no, let me now go to Bungie. Okay, so right, so what's the Fargues-Fontaine curve? So the Fargues-Fontaine curve, it's actually not one curve, but it really depends on some auxiliary datum. And so the auxiliary datum is some algebraically closed field of characteristic P. So let F be a complete, let's say algebraically closed, non-Archimedean field of characteristic P. So for example, this might be, I mean, the simplest possible choice here would be start with the simplest non-Archimedean field in characteristic P, which would be the ring of Laurent series of FP. But you needed to make it complete and algebraically closed. So you take an algebraic closure, but that's not complete. So you complete it, and then it turns out it's still algebraically closed. And so, okay, let me fix two things. So in here, I have the ring of integers OF, and I fix something called a pseudo-uniformizer. So just some topologically nilpotent element. So for example, this element T here would qualify. And then the Fargues-Fontaine curve is the following gadget. I realize that I will now also call this X. Well, sorry. The Fargues-Fontaine curve is the following construction. You take the ring of bit vectors of the ring of integers of OF. You remove the locus where P is equal to 0, or where the Teichmüller lift of pi is 0. This condition doesn't depend on which choice of pi you make, because if you have two different choices, then one divides the power of the other. And acting on this, you have a Frobenius action, and you take the quotient by this Frobenius action. So let me actually draw a picture of this in the equal characteristic case. So this is a Fargues-Fontaine. So if we replace, so the Fargues-Fontaine curve somehow really it has two ingredients. It has the field F that I've just mentioned, and it really also implicitly has a field QP in it, and the field QP somehow manifests itself here in taking the width vectors of OF. So the width vectors are somehow lifting a characteristic P algebra to ZP. And then if I invert P here, as I do by removing P equal to 0, I'm somehow over QP. So I should maybe say that what kind of object is this? So this is an adic space over QP. And it's very much a curve in that locally it's the adic spectrum of some principal ideal domain. But let me rather draw a picture which will make it clear why it's a why it is a curve. So if we would replace QP by F belongs series 2, F belongs series U, then we would get some of the adic spectrum, and some of the width vectors are now replaced by some completed tensor product with a ring of integers here. So you somehow take power series U, and then you remove the locus where P is equal to 0 and where pi is equal to 0. But now there's no Teichmüller lift really anymore, because pi is now literally an element in OF power series U just by the algebra map. And then out of all of this, I'm quotienting out by the Frobenius section. So how does this look like? So, sorry, and P of course has become U. So, so OF power series U, if I take somehow, if I invert pi here, so I'm base changing this to the generic fiber over F again of this thing, then I get some, so this is, let me start. So if I just take SPA of this power series algebra and remove the locus where pi is equal to 0, then this here is an open unit disk over F. If I also remove the set where U is equal to 0, then I get, I remove the locus where U is equal to 0. So instead of this, I get now the set of all U such that the absolute value of U is strictly between 0 and 1. So I get this kind of picture, I don't know, open unit disk and then I have the absolute value U, which gives me some parameter. So the absolute value of U maps this to the open interval from 0 to 1. And I have the Frobenius acting here, which will correspond to multiplication by P. And I'm never sure about the sign, plus or minus 1, on this open interval. And so if I take the quotient by Frobenius, and this somehow means that I'm taking an annulus here, where I'm bounding the absolute value between some radius r and p times r. And then I'm folding together the two boundaries of this annulus. So mod Frobenius get some annulus with boundaries identified. Okay, so this does look like a curve, but I should say one thing is that I was a little bit sloppy in just writing the Frobenius here. And there are really two Frobenia you might think about. So the one is the kind of one which sends U to the P, which in this geometric picture here would somehow be the usual one you would think about, because you're thinking of this as an open unit disk over the field F. So you wouldn't want your Frobenius to act on the base. But that's actually what the Frobenius does. In the arithmetic situation, U would be P, and you cannot act on P. So the only thing you can act on is F. So you have the Frobenius on this part. And so the quotient you take by Frobenius here is actually one which makes a quotient into something that's not anymore an adic space over the field F, but is something that only lives over this other field. F belongs series U. And so, although locally this is somehow isomorphic to some usual kind of rigid analytic variety over this field F, globally it's not a rigid analytic variety over this field F. This closure. That's a little funny, this construction. So. Let me write this down. So XF, F belongs series U is not an analytic space over. If it was over F, then it would somehow be of finite type. So it would really be some usual curve over it. As an analytic space over this other field, it's really not a finite type at all. So you can actually compute, let's say, I mean, I find all of this less confusing if you're really working with a QP, because then it doesn't, this analytic space is really 1 over QP, so it doesn't stand a chance of living over this characteristic P field. And so you cannot get confused about the 2 directions. So a few facts, basically all due to Fargues and Fontaine. So let me list a few. So what are the global structures, functions of the structure sheaves? They are really just QP always, no matter what the field F is. You can also compute the tau fundamental group of XF. And that's actually isomorphic to the absolute Gerber group of QP. Okay, so it's easy to build a map in one direction because it lives over QP. So whenever you have a finite extension of QP, you can somehow pull it back to the curve over it and get something, some finite tau cover of the curve. But over the curve, it really looks like well, geometric covering in that all the residue fields of XF at what one might call classical points are, so which in this other picture would really somehow correspond to the classical points over this field F here, are algebraically closed complete extensions of QP. So, right. So locally, it really looks like something geometric, and that it lives over some complete non-Archimedean field. But globally, it only lives over QP. I should maybe say that which ones are these? These are precisely those complete non-Archimedean extensions of QP whose tilt, in the sense of some perfectoid fields, is this given field F. Okay. Another is that I feel like there's something more limited I want to say before I move on. Well, anyway, you can classify the G bundles. So, I mean, in the original paper, book of Fargues and Fontaine, they classified the vector bundles, and then there's a later paper of Fargues where it classifies all G bundles for all reductive groups G. On XF up to isomorphism. And there is some given by something that's well known in some other in this study of the reduction of Shimura varieties, and also partly in the local Langlands summer, given by Kottwitz's set that's called B of G, of G bundles on of G isocrystals. So equivalently of sigma conjugacy classes. Not in G of QP, but in something called G of QP breve, where QP breve is somehow the completion of the maximal unramified extension of QP. So you have QP unramified completed, or said a different way, you take the bit vectors of FP bar and invert P. And sigma, I mean, there's a Frobenius acting on this, and this is called sigma in this business. So you have the sigma conjugacy classes in this field in G of QP breve, and turns out that this is actually a discrete set. So each sigma conjugacy class is open, and it's somehow really a discrete set, so countable set, and has an explicit combinatorial description. So in particular, again, the isomorphism classes of G bundles also don't actually depend on the field F. They're always the same. What else do I want to say? Right, maybe I should say that for any, still about the set B of G, this will become important in a second. For any B in the set B of G, we have a new algebraic group, GB, which is actually the sigma centralizer of B regarded as such a sigma conjugacy class, or as a representative in this conjugacy class. Then there's a definition. There are different ways to say it, but one way to say it is that B is basic if GB is an inner form of G. So it turns out that there's actually a very interesting procedure to produce inner forms of reductive group G, is to start with such a basic G isocrystal and consider the corresponding sigma centralizer of B. So when you try to study explicitly Jacqui-Langlands correspondences, so between a quartus split form and its inner forms, turns out that this kind of Jacqui-Langlands transfer between representations actually depends not only on the inner form, but how you got the inner form. And there's a series of Volgen of the pure inner forms. And this series of these GBs here, coming from isocrystals, actually generalizes these pure inner forms of Volgen. And you can actually, when you have realized your inner form as coming from such an element in B of G, you can actually write down a canonical Jacqui-Langlands correspondence. So this was something that Kaleta has worked on recently. Okay, so right. So for any such complete non-Archimedean field in characteristic P, we have this Fargue-Fontaine curve corresponding to it, and we can somehow study the G bundles on this funny curve. We would really like to have a moduli space of those, and this can also be defined. So, but to define this, you need to first of all define some of families of the Fargue-Fontaine curves. And usually, if you have a curve over some field, then the way you, over some field K, then if you want to define, look at families of G bundles, then you would look at a K algebra, base change your curve to this K algebra, and then look at G bundles on that. So naively, what you would think you should do is that you look at the moduli space on QP algebras, and to any QP algebra, you associate the G bundles on some of the Fargues curve base changed to this QP algebra. Let me emphatically say that it is not what we do. Instead, you're really using the freedom that somehow F was allowed to vary in a sense, and enhance this freedom. So, so it turns out that you don't actually have to assume that F is an algebraically closed non-Archimedean field. You could do this for any so-called perfectoid field, or even more generally, you can do this to any perfectoid algebra. And somehow repeats the construction, and this is what we'll actually do. So, so for any, let's say, perfectoid F algebra, which in this case, this word perfect is where when perfectoid in characteristic P is actually not such a difficult concept. It's just being perfect. It's just a perfect Banach F algebra. Right, perfect means that X maps to X is a P is an isomorphism. Plus a certain subring which generalizes the ring of integers in F. We can associate the curve somewhere over this R, and really maybe for this R plus, and it just repeats the construction. So you take the spectrum, the adic spectrum of the Witt vectors of R plus, you remove the locus where P is equal to 0, or the Teichmüller lift of pi is equal to 0, and then again quotient by the action of Frobenius. And really, this somehow becomes a functor. You can make this into a functor which maps the affinoid adic space to this curve. And this is called the relative Fargues curve. So, just like in the case of fields, this doesn't actually live over this base field, although it turns out that there is a canonical map from this relative curve on underlying topological spaces. But it's not a morphism of adic spaces. It gives a morphism of what I call diamonds, but up to a small cheat, but really not of topological, not of adic spaces. And so, if in the sense of topological spaces, you somehow take the base change to a point of the base, which somehow corresponds to a perfectoid field with a map from R, then the corresponding base change here would be the Fargues curve for this field. So in this sense, it's really a family of curves. Okay, and so really have a functor which takes the perfectoid spaces S over maybe my base field F to some adic spaces. So maps this S to the relative Fargues curve over S. And then you can define this, the stack Bun-G. Now it's the obvious definition. So it's a stack on perfectoid spaces let's say over a fixed space field F to groupoids. And you send any S to the set of G bundles. On XS. And yeah, so some on first approximation again, if you want to understand this, then you should understand again what the geometric points are. But the geometric points just correspond to other fields F. And so on geometric points, some of this classification result for G bundles already tells you that the points up to isomorphism, so if you collapse this to a set, it's still given by your good old set B of G. So in particular, the underlying space of the stack.
Excuse me, and what is the topology, like in perfectoid spaces?
The stack for which topology?
Yeah.
I mean, you can for the moment just think about pre-stacks if you want to, and not worry about any topology, but it's actually a stack for the finest possible topology you can think of. So there's some of the canonical topology in Grothendieck sense you can put on perfectoid spaces, and it's even a sheaf for that. So more concretely, like let's restrict maybe to these affinoid perfectoid spaces, the ones really coming from pairs R plus. So you can define covers to be all maps which are surjective on topological spaces. So this would be like saying in algebraic geometry, a map is a cover if it's surjective on underlying topological spaces, which seems like a very, very weak condition, and indeed is much too weak in schemes. But you can do it here, and it is a reasonable topology, and it is a stack for this topology. This is called V topology.
Oh, thank you.
Stack for the V topology. So this is all surjective maps. Of spar pluses. Okay, so so let me, before I try to discuss what kind of geometric structure the stack has, I mean, it is a stack for a very strong topology, but in what sense this is an Artin stack or anything like this? Before I try to discuss this, I need to somehow make it clear that it's a very strange object, and that's best by first discussing some substacks that it has. So, so that's a theorem for myself. And I should maybe say that heavily builds on the previous work of Kedloy and Liu, which considered the case of vector bundles. So they considered the case of G. So, right, so the first is that, I mean, in general for G bundles, you have a notion of semi-stable bundle. And so you can look at the semi-stable locus inside of bun G. And this is actually an open substack. And sorry, I should also say that B in B of J is somehow semi-stable in the sense of semi-stability of G bundles, if and only if B is basic. So this notion that Kottwitz defined for these sigma conjugacy classes somehow has a geometric interpretation, and it corresponds to the semi-stability of G bundles. So you have this open substack of G bundles, and you can actually completely explicitly describe the stack of G bundles. It's a disjoint union so somehow by this remark, some of the points are really just all the basic elements of P of G. And then what are what do all the correspondence correspond to? They are somehow all correspond to open and closed substacks in the semi-stable locus. And each of them is just a classifying stack for this periodic group GB of QP. So in particular, if you take for B the trivial elements, and you see that the stack point mod G of QP is an open substack. Well, it's open and closed in the semi-stable locus, and then this in turn is open in Bun-G. And so this is coming back somewhat to the very first discussion. This will be how the representation theory of G of QP will somehow embed into the sheaf theory on Bun-G. And this is some of the locus, where the G bundle is trivial, And so the automorphisms of the trivial G bundle are this group G of QP. And you should note that this is very different from what happens usually in geometric Langness, where the locus of trivial bundles would be the classifying space for the algebraic group G, not the QP value points. So you really get this periodic group G of QP here, not the algebraic group G. And this is related to someone not doing the naive families of Fargues curves, but using the ones where you somehow repeats the construction on any perfectoid space. Right. But this also means that, generally, what is a sheaf on point mod group? It's a representation of the group. And so the sheaves that we get here are really just representations of G of QP. And we're not geometrizing them further in any interesting way a priori. Often when you say, look at representations of finite groups of Lie type, then there is a series of character sheaves where you somehow write the corresponding trace as trace of Frobenius on some sheaf. But we are not doing the thing here where we replace representations by sheaves. We keep the representations. We're not replacing. We're not applying the sheaf function dictionary, is what I want to say. Okay, so what else should I say? So maybe I should say that for any B and B of G, you get the corresponding substack of Bun-G where you somewhat have the fixed vector bundle. And this is a locally closed immersion. And this here is a classifying space for some more fancy thing called, well, for fanciness I write in curly script, which has this periodic group as a quotient. But then here's some kind, let me just write some kind of unipotent group. So the kernel is really more like an A1 or something like this. So it's really in the geometry that we're in, it's really a connected thing. And in particular, if you look at representations here, so if you look at whatever this will mean, stack of analytic sheaves on one of these strata. So this is P of GP. This will still be just the derived category of smooth GB of QP representations. So on analytic sheaves, you don't see this complicated kernel here. And so this means that in total, and so I didn't yet define it, but it will mean that this whole category of algebraic sheaves on Bun-G admits some kind of infinite semi-orthogonal decomposition. With some graded pieces. Something purely representation theoretic. So you derive category of smooth GB of QP representations. Okay, so the geometry of this whole Bun-G is somehow putting the representations of all these different associated groups, some inner forms of G, some other things, into the one big category. And so all the pieces can be described in purely elementary terms, but gluing between the different pieces is highly non-trivial, and I have no idea how to describe it in the elementary terms. Okay. The other thing I should say is that some part, I want to make a claim, which is actually a theorem once you made the correct definitions, is that, due to Fargues myself, that Bun-G is an Artin stack. In the relevant perfectoid sense. Okay, so this may seem a bit weird because what do you imagine an Artin stack to look like? You imagine that it looks like état local or smooth locally like an affine space or something like this. But a periodic Lie group doesn't at all look like an affine space. Not like an algebraic affine space. Like a periodic Lie group is not locally connected, whereas an affine space would be locally connected, and so on. So, but we're not actually claiming that the periodic Lie group is smooth. We're claiming the classifying space is smooth. And so here's a proof that something as weird as a point mod GLN G of QP is an Artin stack. So I have to give a presentation for this. And what I can do is so G of QP actually embeds into G as G itself was an algebraic group of a QP, so you might as well consider it as, say, an adic space of a QP. And then to pass into this world of stacks on perfectoid spaces, there's this funny operation called taking the diamond. But this thing should definitely qualify as smooth. And this here would be a closed embedding, right? So you just take the classical point, the QP value point of this, it's a closed, the periodic topology subspace. And now you have a map from this modulo G of QP, and takes a group quotient, and this maps to G of QP. And so this here is a quotient of something nice. By a locally, in this case even smooth, by a locally pro-finite, in this case even pro-P group. So this bungee, it will live in this world of so-called diamonds, which are quotients of perfectoid spaces by Pro-Étale equivalence relations. And so here is an example of some quotient by some kind of Pro-Étale, pro-finite equivalence relation. We're not taking a quotient by a finite group, but really by a pro-finite group. But it's still well behaved in that setup. And so this is a diamond. And actually, there's a general statement that if you take a quotient of something smooth by a free pro-p action, it will still be smooth in the relevant sense. And so this guy here will be smooth. And I claim that also this map is smooth because the fibers of this map are G, or G diamond, which is also smooth. And so you found a smooth surjection from something smooth onto your stack. And so this means that this guy is an artist.
Sorry,
Okay.
Peter. So vector bundles on this Artin stack correspond to what?
I don't talk about vector bundles here. Sorry, what?
So vector bundles on this stack. What is this?
Why do I care about vector bundles?
Don't care. You don't have the description.
I'm not sorry. Maybe. I mean, there was one thing I did. I was looking at this bungee, which for GLN might be a stack of vector bundles on the Fargues contained curve. But then I was just looking at a certain open substack of this point mod G of QP. But now I don't want to take any more vector bundles on that. I just want to understand this stack, not vector bundles on it.
Okay.
I mean, you want analytic sheaves on this, right?
I want analytic sheaves on this, right? Yeah.
Yeah, well, but still.
Okay. I mean, there's a thing that, I mean, you can consider vector bundles on this, I guess. Yeah, I don't know. There's something.
Yeah, probably something in terms of representations of G of QP. I don't know.
Right.
It's natural.
Yeah. Okay, but so this means that the kind of geometry that you're working with here is really quite strange. So you're really allowing something that might appear still quite nice, such as just as usual algebraic group G, but then you're taking these very wild quotients by such profinite groups and still try to work with those. And you need to, extend your analytic formalism to this. So let me now come to the last part maybe of my talk. So I want to define some category of analytic sheaves. And here is a key problem. This category is not generated by any conceivable notion of what one might understand by constructible sheaves. And this is actually something that comes from the representation series. So namely, if you look at the full subcategory of some the smooth G of QP representations as above, this is generated, as I said, by these compact inductions from some, say, compact open subgroups of G of QP. But these are highly infinite dimensional, right? And they're not even admissible. So not even the fixed vectors under some other compact open subgroup would be finite dimensional. So this is really a very big representation. And we need to allow these very infinite dimensional representations in this category. So in particular, stalks, if you look at this representation and take a stalk, so this means look at the underlying representations. Stalks are some infinite direct sum of copies of QL bars. Okay, and this is not something you would usually allow in any kind of analytic formalism. So,
I'm sorry,
so
but they find that if you consider them as models of the Bernstein center of the category, which is like finite
if you
dimension.
consider them, yes. They have some finiteness properties. Yeah, they are finitely generated over the Bernstein center. But
Yeah.
even then, they're somewhat admissible relatively over the Bernstein center.
Mhm.
But even an admissible representation is still infinite dimensional.
Sure, sure.
You somehow go all the way. So even, yeah, you need to definitely allow sheaves with infinite dimensional discrete QL bar vector spaces as stalks. I mean, so let me maybe briefly recall. So the usual procedure. So one is you define some category of état sheaves. Then you set this to be the limit over all n of the categories with d mod L to the nz coefficients. And then, so if you want to go to QL bar coefficients, you take this and you tensor of this QL bar. And then maybe you also take an idempotent completionist if you want to. I don't know how to denote idempotent completion. But I mean, if you do it like this, then if you do this to a point, this is somehow related to QL bar Banach spaces. Because if you do it with ZL coefficients, then you somehow have something analytic complete, and then you invert L, but only algebraically at the end. So somehow, when you have a morphism, it still will preserve the lattice up to isogeny. So you're producing this way something that's rather has something to do with QL bar Banach spaces. And so if you would proceed like this, we wouldn't end up with representations on QL bar discrete QL bar vector spaces. We would end up with representations on Banach QL bar vector spaces, which is not what we want to study in local Langlands really. So this would somehow raise all these questions, whether a given irreducible smooth representation has an invariant lattice, analytic lattice, how many of these invariant lattices are there, and so on and so forth. Questions you don't really want to address. The usual way to correct this behavior on the point is that you define some of the full subcategory of constructible sheaves, and then again takes the incompletion of this. So then everything is somehow filtered colimit of these constructible sheaves, and this is again a well-behaved category. So in particular, if you do this thing on a point, then the first step would restrict to some perfect QL bar complexes again, which have a canonical structure as some Banach QL bar complex. And then if you take the incompletion of this again, you get all the usual derived category of QL bar spaces. But this correction is somehow not available to us because even the most basic objects we are interested in don't have a structure as a QL bar Banach. Like these things here, they don't have an invariant lattice. And so, well, they have an invariant lattice, but we don't somehow want to pass the completion of this. We really want the discrete guy. And right, so this way to correct it in the end is somehow not available to us, and we somehow need to proceed differently. So let me say a few words about how this is done. So the first step in this procedure is somehow more or less the same. So that's something that I've done a while ago in a manuscript called Étale cohomology of diamonds. So there, for any kind of V stack, Y, I define some derived category with C mod L to the n coefficients. Let me actually say one word about this definition. So let's say maybe consider the case where so these V stacks, they always have presentation in terms of diamonds. So if you have a diamond, then you can always write this. You can always find a pro-Étale surjection from some X, which is a perfectoid space. That's basically how these things are defined. But this means that diamonds, in general, they don't have a nice Étale side, because you don't really have Étale maps into Y. You only have such pro-Étale maps into Y. And so the way you then actually define this category D at Y C mod L to the n is actually as a full subcategory of somehow the side corresponding to the pro-Étale side of this diamond, C mod L to the n coefficients. Of those objects that somehow after pullback to X come from Étale sheaves. So perfectoid spaces, they have nice Étale maps. Okay, so really the way this definition from all this time has worked is that to access some of these weird geometric objects, these quotients by pro-Étale equivalence relations, you're really forced to contemplate the pro-Étale side of these guys. And then at some later point, restrict back to some more well-behaved category where you can actually define six-functor formalism. So if you tried, so the six-functor formalism doesn't actually, so I should say, and the six functors. And the six functors, they are somehow six functors.
Peter, I'm sorry, I got confused. What's the difference? Sometimes you write D, sometimes you write D subscript étale. So what's just plain D?
The plain D is something that hasn't been defined yet. So if I write D of 1 GQL bar, say, this is something that hasn't been defined yet and that will come up later.
But the next page, I mean.
So here, this is the classical definitions.
Yeah, no, I mean, page after, so just the last page you wrote here, yes, with the Y.
So here, but here there's a Y pro-Étale, so that this is the usual way to define, like whenever you have a ringed side or ringed topos or whatever, there's a derived category of sheaves.
Great. And now, and on the left-hand side, you have D sub étale. What does this? This
is a definition of what this D at means. So if Y happens to be a perfectoid space, this would, maybe of finite dimension in some sense, this would literally be the derived category on Y étale with C mod L to the n coefficients.
Mm-hmm. I see.
But then you want to descend to these more wild objects, and then you somehow have to say where they a priori live, and then.
Aha, so for Y perfectoid, you're making a distinction between sheaves on the pro-étale side versus sheaves on the étale side. Is that?
Yeah.
Okay, thank you.
But I want to make the point that, like, if I would only think about perfectoid spaces, there wouldn't probably be any point of ever thinking about the Proital side, but you actually somehow are forced to do it within the kind of geometry that you're in here.
Thank you.
But on the other hand, if you want the 6 functors, there is something that really only exists for the État sheaves, not all Proital sheaves. And so, yeah, one can extend then everything to just formally passing to the limit over all n. This is d at y z mod L to the n. But this is not good enough for us. So you actually need to find a larger class of Proital sheaves for which this kind of 6-functor formalism is sufficiently well behaved. And so neat. So what you can actually always do is you can look at the Proital side of y. And I mean, on the Proital side, there is an interesting sheaf ZL, which is almost inverse limit of all the constant sheaves Z mod L to the n, which is now not a discrete sheaf anymore. It's not a constant sheaf anymore. And certainly all the sheaves that one ever cares about, they will live in here. So this is a really huge category. So in particular, this will contain some kind of infinite direct sums of ZLs or QL bars or whatever. But the whole category is somewhat not well behaved enough because you don't have Poincare duality for this kind of setup. So you need to pass to a larger subcategory of this where you can still retain Poincare duality, but on the other hand, don't just have analytically complete complexes, but more than those. Right. So retaining some direct sum of QL bar, but obtaining Poincare duality. And so this actually leads to a story which is somehow already interesting if y is just a geometric point. So this quest is already interesting. And this is a context of what Dustin Clausen and I termed condensed mathematics. And which is some replacement for topological mathematics. So mathematics with topological objects. And it's based on the following thing, which is somehow completely implicit in this formalism of diamonds and so on, but somehow really deserves to be studied on its own, namely the condensed set. Is just a sheaf on the Proital side of a point. So this is somehow the category of profinite sets and finite families of surjective, jointly surjective maps as covers. And similarly to condensed sets, you can then talk about condensed being groups, condensed whatever, condensed rings, and so on and so forth. And right. And condensed structures are closely related to topological spaces, condensed sets. So let me give an example. If T is a topological space, then I can define something I call T underline. It's a condensed set, and it takes any profinite set S to the continuous maps from S somewhere as a profinite set to T. This is a condensed set. Where let me take the freedom here of ignoring some set theoretic subtleties. And this functor is not too far from being fully faithful. So on compactly generated topological spaces, so for example, on metrizable ones, it's fully faithful. But on the other hand, condensed sets have much better categorical properties. So for example, they have an internal Hom object. So whenever you have two topological spaces, there's usually a whole industry of trying to find a natural topology of maps from one topological space to the other. This maybe the compact open topology is the most favorite one. But in functional analysis, there's really a whole zoo of such. In condensed sets, there's really a completely canonical structure of condensed set on the internal Hom. Because you just have internal Homs in this category. Also, condensed Abelian groups form an Abelian category, just as sheaves of Abelian groups on any side do. But they have some additional niceness properties. So, for example, it's a compactly generate. The condensed Abelian groups are generated by compact projective objects, and so you actually have projective resolutions still available. And I mean, there's really a whole lot of stuff you can do, and it works beautifully. The only thing that works a little funny is when you try to form tensor products. So if you try to form ZL somehow as a condensed Abelian group and tensor it with CP as a condensed Abelian group, and CP is not equal to L, then this is some funny nonsense. I mean, the underlying Abelian group, meaning the value on a point, is still the good old tensor product of these two Abelian groups, which is some huge Q vector space. But you sense that there should be a notion of completion of this tensor product, such that if you complete this tensor product, it should be equal to 0. So there should be a notion of completion of condensed Abelian groups, so a notion of complete condensed Abelian groups that somehow rectifies this behavior of the tensor product. And indeed, there is such a notion, and this is what Clausen and I termed solid Abelian groups. And there are several ways to say it. Maybe the one way to say it is the following. So if for any map S from N to M, where S is a profinite set, so it's really somehow a limit of some finite sets Si. There exists a unique extension F tilde from what we call the solidification of the free condensed Abelian group on S, which is defined to be the limit of the free Abelian groups on the SIs to M. So note that you have a map here from the inverse limit of the SIs as some of the basis elements, which is S. So S maps into here, and this map is supposed to be okay, so you can make this definition, and it turns out that, and this is highly non-obvious, that solid Abelian groups form in a being category. And subcategory. Some are stable under kernels, co-kernels, and extensions. Particularly in the extensions. But also all co-limits and all limits. The most surprising statement here is maybe that they're stable under all co-limits, because usually you wouldn't expect all co-limits, all direct sums of complete things to be still complete, but it happens to be the case here. And on the other hand, you can compute many interesting tensor products. So if you take ZP tensor ZL, and so there is a solidification functor. A left adjoint to the inclusion.
Sorry, for example, Z of S dot, is it an example of a solid group within?
Yeah, so this is actually the solid. So like in any topos, whenever you have a condensed set, there's a free condensed Sabine group on it. And so in particular, any profinite set is a condensed set. And so you can take the free condensed Sabine group, which we call Z adjoint S. And the solidification of this is will turn out to be the same, essentially by this universal property action.
Thank you.
But now you can compute that now two different primes cannot talk to each other. Take ZP tensor ZL, the tensor product is equal to 0. Okay, and
so usual simple topological groups, like a circle, is it solid?
So good question. So so Z itself is solid, and everything you can build by limits and co-limits from it is solid, which includes basically everything you can construct, except for two things. You can get new things by forming tensor products, and those in general you have to solidify. And there is another standard example of a topological group, namely the real numbers. And the real numbers are not solid. And in fact, if you try to solidify them, they just become 0. So the theory of solid abelian groups is very much a non-Archimedean theory. And it has taken us a lot of pain to figure out whether there's a similar notion of completeness also for real vector spaces. And it turns out that there is such a notion. We call these liquid vector spaces. But it's a really interesting and quite deep story. And you can read it in the lecture notes to my last course on analytic geometry. So. The basic problem in this story of the real numbers is that condensed sets, condensed Sabine groups, and so on, they are very much based on profinite sets. So if you try to compute an X group, you need to take projective resolutions, but these projective resolutions, they will be somehow built by the free objects on profinite sets. So you have to resolve everything in terms of profinite sets if you want to compute something about condensed Sabine groups. But if you have the usual real vector space, a topological real vector space, then you don't want to resolve this by profinite sets. But you have to if you want to somehow prove these results on real vector spaces. And so this actually makes this a very delicate endeavor, but it works. But gives rise actually to some quite fascinating structures. Anyway, so this is not the topic of this talk, which is about the solid stuff. So somehow it turns out that there is this really nice notion of these solid abelian groups, which is some very algebraic notion of like a complete topological abelian group somehow. But it has really nice categorical properties. And it turns out that and maybe I'll do this in briefly. So the upshot is that also relatively on something like Y pro et al, where Y is some diamond, we can somehow define the solid CL sheaves. You can actually do this as well with all the BN sheaves, just because you somehow need to stick to this prime L. But once you just ask for a module structure over ZL, this is perfectly well. Maybe I should have given an example, yeah, of solid things. So Z is solid, but also ZL is solid, or a direct sum of QL bars is solid, but also a direct product of QL bars is solid, and whatnot. Yeah? I mean, everything you can build by limits and colimits. By taking quotients, all sorts of non-separated quotients are also okay. Yeah? So, yeah, in particular, this notion of solidness also gives it a completeness notion for highly non-separated things, and so on and so forth. So you can define these solid ZL sheaves. Let me denote this by D solid YCL. So this will now contain something like a direct sum of copies of ZL, but it would also contain a direct product of copies of ZL, and lots and lots of other stuff. Okay, so this is a really huge category, but Poincare duality holds. So you can essentially extend the six-functor formalism to all these solid sheaves. But now you somehow, in some sense, shot too far because the category is way too large now.
Question. Is this somehow related to Pozitselsky's contramodules?
This is not related to, no, this is not related to derived analytic complete things or anything like this.
No.
I mean, as I said, somehow an infinite direct sum of copies of ZL is okay.
Mm-hmm.
You don't need to analytically complete again.
Right.
But now you somehow found a very big category where at least all the functors are somehow behave as they should. You have Poincare duality. And then somehow, as a last step, you can somehow then isolate the category of those sheaves that you actually care about. So as a last step, which is somehow in some sense the analog of the step of passing to this DBC of XQL bar. So maybe I should have said, so these solid LCL sheaves, they're again a full subcategory of all sheaves, of all Preutor sheaves, CL coefficients, and there's again a left adjoint to this. And some solidification functor. It takes a full subcategory. Let's say if Y is some kind of Artin stack. Let me call this D-list because it's in some sense, or kind of suggestively call it D-list-ital because it's a little what it feels like. Let's say we work with CL coefficients still. Everything works with CL coefficients. You can still in the end tensor to QL bar if you want to. In this, well, let me say it like this, define this. As a full subcategory. Generated by a Floor-Schwieg of ZL, where F from X to Y is any smooth map in the relevant sense. And so then actually this DBC of a point. Oh no, let me call this easy. Okay. So in some sense, I mean, if you look at the Lie-et-al side of some Artin stack, then you somehow look at the side of all smooth things over your stack. And the category is somehow by definition generated by some of the sheaves represented by all these axes, which is somehow what you're mimicking with this definition, that some of all these smooth maps somehow should form generators for this category. And you somehow just take this part. And then it actually turns out that there is now a right adjoint to this inclusion. And so you can, again, somehow more or less reflect all your functors that you want back into this subcategory. And now if you do this on a point with the L coefficients, you really get the good old derived category of the L modules. Sitting inside all the solid ZL modules. And these in some sense sit inside of all derived category of all condensed Being groups. And yeah, so in the end, you somehow restrict it back so that on a point, you really just get usual discrete ZL modules. And actually, the way you've realized these inside of all condensed Being groups is exactly the same construction that I did in the very beginning when I discussed the stack of L parameters, where I also, the way this embedding works is that you're somehow, for a finitely generated module, you take the L topology, but then you extend by colimits. And this is how this construction that we do on the sheaves, the side of L-like sheaves, is actually compatible with what we're doing on the stack of L parameters. And so how eventually you can make the connection. Right. And so with this, you somehow get this category, which is somehow this, what I've just defined as these eta, and this QL bar coefficients you take just somehow tensor with QL bar and maybe take an idempotent conjecture. But again, you don't really have to do it. The whole conjecture should work over ZL already. So it's just a more classical thing if you work over a characteristic zero field. And yeah, so this way you can accommodate all the L-like sheaves. Now I'm basically out of time. Right. And so far I've only explained in the conjecture, but maybe if some questions come, I can also say a little bit what one should be able to prove. Okay, let me stop here.
Okay, thank you very much. Thank you. So are there some questions?
Again?
Yeah, okay. So what shall you be able to prove then?
So I don't think it's completely out of reach to take something like this, but what I think that should definitely be possible is the following. So as a first step, you can try to get what's called the spectral action. So you should have an action of some of the perfect complexes on this stack of L parameters on T of Bungie. So there's this paper of Nadler and June on Getty geometric Langlands where they somehow produce such a spectral action in the setting of Betti cohomology, so for Riemann surfaces and yeah, it's the usual topology. And then there's this more recent paper of Gatesbury, Kashdan, Warshawski, and Rosenblum, where they somehow gave some general categorical data, somehow saying what you need to produce in order to get a spectral action. The data that you need to produce is something that somehow you always have at hand when you do geometric Langlands. So you're somehow trying to do geometric Langlands on the Fargues curve. In particular, like for any representation of the dual group, you should have a Heck operator acting on the derived category of Bungie. And what you need to know is that when you apply a Heck operator, I mean, you get, so there's a really Heck operator for any representation of the dual group and any point on your curve. And you need to somehow know that when you move your point on your curve, you really get something that's locally constant with respect to this point. And this is something that we can definitely prove. And so we basically have the categorical data that Gatesbury, Kashdan, Rosenblum, and Warshawski tell us is equivalent to a spectral action, with two caveats. One is that the group that's acting, the Weil group, it's not a discrete group, so there it's in the setting maybe of usual discrete groups there. So we have to somehow accommodate the Weil group, but this is somehow taken care of by all this condensed formalism, by all this Proital size and so on. So that's not too serious. The other that one has to think about is that we would really like to have this with ZL coefficients. But again, if one just states the right statement, makes the right statement. I mean, they're considering characteristic zero coefficients, but I think if we just does the right thing, it should also work with ZL coefficients. And so then you get an action essentially of the right-hand side, except that the stack is just a complete intersection. It's not smooth. So there's a difference between coherent sheaves and perfect complexes. But yeah, you can also somehow guess what the structure sheaf should correspond to. It should correspond to some of the Whittaker representation. And so you should basically get a map from left to right, except for this issue of pro versus perf. Yeah, I haven't really thought about how to prove that this is an equivalence. But you definitely get the spectral action, and this already implies that whenever you have an irreducible representation of your periodic group, you get an associated L parameter.
So, Peter, can I ask? So I can imagine so that for GLN, one would be able to prove the equivalence using, well, this standard Whittaker/Mirabolic trick. Do you expect to do arbitrary group?
I don't know. I mean, there is this approach that you outlined, how to prove geometric Langlands, right? You embed into Whittaker things, and the Whittaker things should be equivalent. And
yeah. But so this outline hits a wall for groups other than GLN because we don't know that the Whittaker model, well, captures everything.
What does, sorry, I didn't really study any of this in detail so far. So there seem to be two things. The one is showing that the spectral and the kind of representation theoretic Whittaker categories are equivalent. Is that already a problem?
No, that's okay. This
okay.
is fine.
And so you already know that both sides embed into full subcategories of something, no?
No, we don't know that the category in Bun-G embeds into the Whittaker model. So we don't know that cuspidal stuff doesn't get lost when you go into Whittaker.
I see. Well, I mean, maybe one has
and
more hope here because
that's the main obstruction.
I don't know. I would have to think about it. But one good thing is that the cuspidal part of this D-Bun-G, it's purely representation theoretic. So it's purely concentrated on the same as stable locus. And is somehow purely given in terms of representation somehow of G of QP and its pure extended pure NF forms. And so you can hope to use all the results that people have established in usual representation theory to take these kinds of questions. But it's not something I've started to think about.
Let's hope.
Just a quick tip. So for GL1, it works tautologically, right?
Not tautologically, but there's a paper of Laurent Fargues where he proves that everything works for GL1.
Okay. And also a stupid question maybe. Is there something like a Hitchin system for the curve?
A Hitchin system.
Yeah.
Well, there are no differentials on the curve.
Right, so there is no analog of anything of abelianization going on here. Because I mean, one approach which was dictated by physicists a long time ago is that you look at the Hitchin system, which is like an abelian vibration, and then essentially you reduce GLN to GL1 by going to this.
Right. I would be surprised. So you can talk about D modules on the curve. You can talk about Higgs things. I mean, there are no differentials on this curve.
No, obviously right away doesn't work. I mean, I understand.
Yeah. So yeah, I also don't see any analog. I mean, actually, how does this work if you try to, maybe Dennis knows something about, I mean, if you try to prove Betti geometric lengths, are there any techniques like, I mean, D module doesn't really help because you have integral coefficients and so on.
No. So for D modules, the huge advantage is that there are two constructions. One is Whittaker, the other is D modules basically via generators and relations, and
Right.
Hitchin system is just kind of fancy way to incarnate that, and you can play one against the other, and then you can prove more stuff.
Right.
But Betti and Eladik, you only have half of these methods, so
Yep.
you're more restricted.
Right. So yeah, but I mean, still, I mean, so the really new thing you get in some of your periodic representations, some representations of periodic groups, is that you can use all the techniques from geometric Langens, all the which are not really pure D module. You can now apply in this setting, and this really gives you quite a bit. And I mean, I didn't talk about this, but you can really mimic a lot of the geometric Langen stuff. In particular, it gives an explanation for both where the dual group comes from and where the Weil group comes from in local Langen. So the dual group really comes from geometric Satake. So there is some, if you try to define the Heck operators on band G, then in the usual way, they will be somehow given by these modifications of G bundles. So by the, there's the FN Grassmannian entering the picture, and you need to somehow put some kernels here, so some perverse sheaves as kernels, and these equivalent perverse sheaves on the FN Grassmannian are just equivalent again to representations of the dual group. So that's where the dual group comes from.
Sure.
And also, like, you need to move your Heck operators are parameterized by points on the curve, but as I said, the fundamental group of your curve is just the Galois group. Actually, turns out that the way the formalism works out in the end is rather the Weil group. And so that's where the Weil group action comes from. The Weil group. And then just purely from the existence of such Heck operators, by some purely categorical formal procedure, you just get L parameters associated to irreducible representations.
And again, very stupid question. So is there any chance for like periodic version of stuff?
Is there any chance for a periodic version of this? Very good question. I hope so. But it's far from clear and far from easy. So the issue is that you would like to have some kind of six-functor formalism now with periodic coefficients for these for this kind of band-G there. But these are very much periodic spaces, and so étale cohomology doesn't work well on characteristic D. So you need to do something more fancy. And but one can guess what the more kind of fancy thing should be, but it will be quite fancy again. In particular, it will again involve some solid sheaves and whatnot. But I have a PhD student who's thinking about whether there could be some kind of six-functor formalism with periodic coefficients for these guys. If there is, there would be hope for having a periodic version of the story, which would in that case actually be much closer, I believe, to the D module geometric Langens.
Is it too early to speculate at least of what the conjecture could be?
It's not at all clear. So I mean, one can make a guess for what the dual side should be. So what should the stack of L parameters be? So recently there is some work of Emerton and G where they define a stack of phi gamma modules. And yeah, one could expect that coherent sheaves on their stack of phi gamma modules should be the thing that's on one side of the correspondence. Although there's already a little subtle to define because their stack is really a formal algebraic stack. So it has to be a little careful about what one means by coherent sheaves on this side of it. But I think this should be mirrored by maybe other complications you get on G side. So I mean, it will definitely be quite complicated. It will also definitely be not true, I think, in the setup that, I mean, this is the same as for D modules. It's not the case that if you move your points, the Heck operators are somehow locally constant. This will also, I think, fail in this periodic story, which will, I think, make things quite a bit more complicated.
Sure.
Yeah, I think it's a far way to go until one can try to make sense of this, but I'm hopeful that there is at least something.
Well, thank you.
Can I ask one final question?
Yeah.
From me. So, is there a notion of singular support for elliptic sheaves on this band? Well, I want to say for some reasonable y, in particular for this band G. And the second question would be, if there is it true that in this particular case, on band G, all elliptic sheaves will have automatically nilpotent singular support? I'm kind of trying to see if this situation is really analogous to band G of P1.
Right. So my problem is that I never looked up what the nilpotent singular support of an elliptic sheaf is. So can you remind me of the definition?
Yes. So you do it for mod L, and then you pass to the inverse limit. So an ZLL sheaf has singular support somewhere if it does mod L. And mod L, it's basically you test by nearby cycles. So vanishing cycles. Basically, over a curve, no single support means no vanishing cycles. And then you can imagine you just move your vanishing cycles around.
Okay. I mean, this kind of geometry, the issue is somehow that you don't really have, things don't look like affine space, and you don't locally have enough maps to an affine line or something like this. So this very definition, I think, is not suitable. Testing against curves in this way. Maybe there, I don't know, but there are probably equivalent definitions, and maybe one of them should work, but I've never tried to find one.
And so another definition, so I don't know if it's like this. So if you have a variety over a base, there's a notion of for a sheaf upstairs to be what's called ULA over the base, universally locally cyclic.
Right.
And I should be more precise. In fact, it's this notion that's used in the definition of singular support. So if you have something like ULA-ness, then you would be able to define singular support.
So being ULA is a property that can be defined. And if you look at these, what I called DBC in the very beginning of my talk, so some of the compact objects in there, not all of them are ULA. But so there's actually an issue here that because some of these generating objects are really quite big, they are not even Verdier self-dual. I need to put electricity in, otherwise I'm lost in the street. Okay. They're not even Verdier self-dual. But you can somehow pass to a subcategory of all the reflexive objects in this DBC. So these will be ULA.
ULA over what?
Being ULA is the same thing as nilpotent singular. No, sorry, what?
So ULA over what? ULA is relative notion. ULA.
You have band G over a point, and you have a sheaf over band G, and you can ask whether this sheaf is ULA with respect to the projection to the point.
So in normal situation, ULA over a point, everything is ULA over a point. You have just in algebraic geometry, you have a variety.
All right, yeah, sorry, that's because I mean everything constructible is.
Everything constructible is correct. Yes.
Right, but here the constructibility, as I said, is a little fishy, and actually not everything is ULA over a base, but you need to impose some things which are admissible at every point. Those things are ULA. That's not all of them.
Maybe we shouldn't. Maybe we can discuss it separately. So yeah.
Some more questions, maybe? If not, then let's thank the speaker again. Thank you very much, Peter. Thank you.
Yes, thank you for the invitation.